Tonight I'll be reading to you a nonfiction book by astrophysicist Janna Levin, Black Hole Survival Guide, with artwork by Lia Halloran, published in 2020 by Anchor Books, a division of Penguin House LLC. Start at Chapter 1. Entrance. Black holes are nothing. Black holes are special because there's nothing there. There is no thing there. I probably accepted black holes whole, as complete conceptual entities, before I was able to doubt, before I had intuition to combat. They were fodder for fantasy. I received the fact of their existence without resistance, gullible, and without prejudice. I could see the plausibility, appreciate the curiosity, their peculiarity, accept the universe as it was presented. Maybe it was the same for you. It's very unlikely that this is your first encounter with the astrophysical oddity that is a black hole. The warp in space-time is so strong that not even light can escape. I don't know what it was like where you were, but I had a pretty unspectacular view, astronomically speaking. Out of my childhood bedroom, I would edge to the foot of the bed and strain to look at the sky through the window frame, a portal to a green yard below, the seams between neighboring plots, demarcated by shrubs or trees, patchwork real estate scooped together under a rounded cap of atmosphere. The ground would darken first, then the trees, but the dome would hang on to the vaguest blattering of light for the longest. Ours was not an urban, burnished sky, but still light pollution diluted the view that I stared into night after night. I never expected the vista to improve, or expected anything new. Only the usual indistinct few bright speckles, like rain stains on a windshield. I don't remember when the feeling started, the first time that longing tugged at me, but before I even recognized the desire, I pined to know what else was out there, like a restless dog pacing at the door. I wanted to be free of ordinary confines, to fly there and explore. Frustrated by the fact of the heaviness of my feet on the earth, striding at the base of the sky, restless to be let in, I wonder how many of us inherited this longing, millennium after millennium, generation after generation, child after child, bound to the crust, wrapped at the illusion of a ceiling, compelled to crack through and defy our puniness and our limitations. As a kid, I never imagined I would become a scientist. If you had told me I would become a physicist, I'm sure I would have been offended. Scientists build bombs and memorize equations. I'm not sure if I acquired that cliché, or if the stereotype was one of my own invention, that scientists could not be creative, or just weren't out of stubbornness. I didn't understand the profound freedom of constrained creativity, visionary originality that explodes in the face of fundamental limits. Limits have incited revolutions. The limit of the speed of light hinted at relativity. Einstein fantasized about riding a light beam and imagined that time stood still. He gave up the absolutism of an inflexible space and time in favor of the absolutism of the speed of light. That concession forced us to reconceive of our universe as an impermanent, living process, with an origin in a big bang, still expanding with the energy of creation, and home to extravagances like black holes. The quantum revolution was incited in parallel by the limit imposed by Heisenberg's uncertainty otherwise have been unattainable. We rewrote reality in an astonishing new language. We have discovered quarks, photons, neutrinos, condensed matter, dead neutron stars, the Higgs boson, superconductors, and quantum computers in the most precisely tested paradigm in all of physics. The computer revolution, too, was incited by a limit, an insurmountable limit to mathematical knowledge. The incompleteness theorems, which proved that there were mathematical facts that could never be proven, led Alan Turing to dream of artificial intelligence and biological machines. Turing proved that most facts about numbers are unknowable. There is an infinite list of irrational numbers, with an infinite list of unpredictable digits. His musings led him to imagine a machine that one day will think, and to the epiphany that, indeed, we are machines who think. The severity of the constraints imposed by physical law and mathematical precision does not squash creativity. The limits are the scaffolding enabling creativity. Limits can be worthy adversaries that galvanize our best, most inventive, most agile natures. Before I succumbed to the seduction of the elegance and transcendence of limits, I did not understand the thrill of imagination crashing into truth. As a student, not yet on a trajectory to become a scientist, I was nostalgic for that longing to leap into the atmospheric pool of blue midnight high out my window. I realized I missed that sensation, the urgent desire to leave the planet. Wherever I was by then, I was still under the same sky. From a slightly different perspective, I trod at the foot of that blue dome, that overly lit blanched blue sky, and wandered in. Deterred by reality, we've never gone farther than the moon. I redirected my focus down to the page, following mathematics to places our bodies couldn't go. Mathematics alone cannot tell us what specifically is out there in our universe. The mathematics can speculate only about what is possible, and sometimes mathematics allows us to explore pure potential before any physical manifestations of that potential are discovered. Black holes were like that, a purely mathematical construct on the page, benign in virtual form, in transcript on paper, unverified for decades, unaccepted for decades, absurd, maligned, denied by some great geniuses of the 20th century, until physical evidence of real black holes in the galaxy was discovered. Find one just a few thousand light years away, a light year being the distance light can travel in a year, nearly 10 trillion kilometers, the distance you would travel driving at the average highway speed limit for 10 million years. Take a left at that yellow star and veer toward that star cluster. Wandering at the base of the sky, we are under them, we are above them. Black holes, in their abiding darkness, are scattered plentifully among the stars, which themselves are scattered plentifully like somber glitter, infiltrating the void. We are in orbit around one in the center of the Milky Way galaxy. We are pulled toward another in the Andromeda galaxy. I want to influence your perception of black holes, to shuck away the husk a bit and get closer to their darkest selves, to marvel at their peculiarity series of simple observations that culminate in an intuitive impression of the objects of our attention, which are not objects at all, not things in the conventional sense. A friend takes me out in New York to discuss the essentials to include in a black hole survival guide. An accomplished science writer, he asks me to clarify, don't I already know everything about black holes? Do you know they are nothing? He looks at me unblinking for a long time, considering. He pauses to toss some salted peanuts into his mouth, and while doing, he says, I guess I don't know anything about black holes. Then, slightly bemused at this realization, we eat the rest of the bar snacks and drink our wine while we talk about things more familiar. Chapter 2. Space. Weightlessness and freefall. Black holes are much maligned, depicted unfairly as behemoths, when they are often benign and actually by nature quite small. Still, before you travel, you should do your research and consider the hazards. The perils, in fairness, are exceptional and unmatched if you are not careful. As with the nature untamed here on Earth, black holes demand respect for safe navigation. After all, you are a trespasser on their territory. Black holes were the unwanted product of the plasticity of space and time, grotesque and extreme deformations, grim instabilities. Honestly, they're not such an anathema to scientists now. Black holes are a gift, both physically and theoretically. They are detectable on the farthest reaches of the observable universe. They anchor galaxies, providing a center for our own galactic pinwheel, and possibly every other island of stars. And theoretically, they provide a laboratory for the exploration of the farthest reaches of the mind. Black holes are the ideal fantasy-scape on which to play out thought experiments that target the core truths about the cosmos. When in pursuit of a black hole, you are not looking for a material object. A black hole can masquerade as an object, but it is really a place in space and time. Better, a black hole is a space-time. Imagine an empty universe. You have never seen or experienced such a pristine place, a vast nothingness that is the same everywhere, vast and bare and flat, still three-dimensional, but everywhere flat. Here is the sense in which an empty universe is a flat space. If you were in flat space, you would float on a straight line. Despite the fact that you are not falling in the colloquial sense, free motion is called free fall. You are in free fall as long as you do not fire any rockets, get pulled or pushed, essentially as long as there is only gravity. Just surrender to space. If free motion can be traced by straight lines, and lines that begin parallel never cross, then the geometry of space is flat. Chances are surpassingly bad that you are in free fall right now. Chances are also surpassingly bad that you are in flat space, since there is no such place anywhere in our galaxy. Sit on a chair and you are not in free fall. The chair pushes on you to stop your fall. Stand on a floor and you are not in free fall. The floor pushes against your feet to prevent your plummet to street level. Lying in a bed, we feel heavy. We say gravity pulls us down, but we have it all wrong. Totally inverted. What you feel is not gravity, but rather the atoms atoms in the mattress pushing against your atoms. If only the bed would get out of your way, and the floor, and all the lower floors, you would fall. And falling is the purest, uninterrupted experience of gravity. Only in the fight against gravity do you feel its pull, an inertia, a resistance, a heaviness. Give in to gravity, and the feeling of force disappears. The classic setting for the idea of free fall is an elevator. You are high up in an apartment building in an elevator. You feel a force against your feet. That force is between your feet and the elevator floor and keeps you in the cab. It's a force between matter. Now, if you are interested in pure gravity without the interference of interactions between matter, you must get rid of the elevator somehow. So you enlist someone to cut the cable. The elevator falls and you with it. During the descent, since you and the floor fall at the same rate, you would float in the elevator. You don't fall to the floor because the floor is falling too. You can push off the walls and tumble in the air. You seem weightless, as though you are an astronaut in a space station. You can pour water out of your water bottle and drink the droplets from the air like astronauts do. You can release a pen, a phone, a rock in front of you, and those float too. Einstein called this profoundly simple observation that we experience weightlessness when we fall the happiest thought of his life. The spoiler is that your atoms interact with the atoms in the Earth's surface, and that would ensure an unhappy end to your free fall when you hit the ground. But that's not gravity's fault. The shattering of your bones would be due to other forces, like forces between atoms. If you were made of dark matter, you could fall right through the Earth's crust and sail on down. We can't run the elevator experiment for long before the Earth gets in the way. So instead, imagine you float far from the Earth, far from the Milky Way. Imagine a fictitious empty space, except for you and your spacesuit. If you sent tracers through a projectile in each of the 3 spatial directions, those projectiles would free fall. Now, imagine each projectile leaves a helpful trail, illuminating its path. Soon, a grid of straight lines would be visible. You could see plainly that space was flat. Free-falling objects follow straight lines, and that space was empty, except for you and your spacesuit and your tracers and the luminous trails charting the grid. Gravity is so weak that none of these little pieces have a noticeable impact on the flat emptiness of it all. The universe is not empty. We are very aware that we are bound to the Earth. The Earth is bound to the Sun, and the Sun to the Milky Way galaxy. The Milky Way is bound to the neighboring galaxy Andromeda, both residing in the Virgo supercluster of galaxies. And the Virgo supercluster senses all other galaxies and all the accumulated energy in our observable universe. So we don't live in a flat, empty space-time. Astronauts also don't float in empty space. They can see the Earth spin and the sun roll along. They are falling and weightless, but on a path we've been accustomed to calling an orbit. An orbit around the Earth, in orbit around the sun, in a glacially long orbit around the galaxy. Their paths aren't straight. Their paths are curved into a circle around the Earth, sewn into a circle around the sun, sewn into the path around the galaxy, because freefall paths are curved when the sky isn't empty, because space is curved by the presence of matter and energy. Curved space. You can prove that you live in a curved space and not a flat space from the comfort of your couch by throwing things. something and watch. The arc it traces. The projectile will not travel in a straight line. The path paints a curve in space, an arc. All the objects we throw follow curved paths toward the Earth. Could travel around the globe throwing projectiles. All objects we throw from international couches will bow to the ground. We could document the results and draw a three-dimensional grid of the curved paths and thereby construct a map of the shape of the space around the Earth. The lesson: the Earth deforms the shape of space, and you can map that shape by drawing freefall paths. Freefall depends on the speed at which you toss something around the planet. Drop a wrench to the Earth, and it follows a line straight down. Throw the wrench across the room, and the descent is along an arc, the same arc a car would descend along if thrown at the same speed and in the same direction as the wrench. Throw the wrench faster, and the arc gets longer. Throw the wrench fast enough, and it will clear the curve of the Earth and launch into orbit. Throw the wrench faster still, and it will float away from the Earth forever, until caught on the curve of another celestial object, like Jupiter or the Sun, and tumble on a different path. Planets fall around the Sun. No engine pushes them. They trace ovals, always clearing the atmosphere. The Earth falls freely around the Sun, and the Moon falls freely around the Earth. The Earth falls freely around the Sun, and the Moon falls freely around the Earth. We put lots of human-made objects into orbits, which are just freefall paths. Once the launched spacecraft gets where they need to be, the engines are turned on and they can fall forever in orbit around the Sun, or more commonly, the Earth. Some mission specialists fight against the inclusion of thrusters in case a decline in funding encourages the space agency to maneuver the satellite out of orbit and incinerate the bounty in the atmosphere. Defunct satellites haunt space, ghostly litter in orbit for the lifetime of the solar system. The International Space Station falls freely around the Earth. The astronauts in the space station float because they are falling like the ill-fitted elevator occupants, not because they don't feel the gravitational effects of the Earth. They do. The station is only a few hundred kilometers high and very much under the Earth's influence. The gravitational effect is traced by curves in the shape of a space, and the ISS follows one such natural curve, an ever-falling circular orbit. The astronauts in the space station travel nearly 28,000 kilometers per hour to complete a full circle every 90 minutes, out of the sunlight and into the Earth's shadow, and out again into the sun's radiance. They move fast enough that they always clear the Earth's atmosphere while falling, and thereby never crash into the surface. From Einstein's happiest thought, we fall in space weightlessly, we deduce, with the most ordinary observations, toss projectiles from the vantage of our Earth-covering couches, that free-fall paths are curves in space. Gravitation is curved space-time. And that insight was Einstein's greatest. Einstein's unabashed devotion to simplicity shows in the childlike wondrousness of his unembellished, spare-thought experiments. He knew he did not understand standard issue grade school gravity. How can the Earth pull on the moon when they're not touching? Einstein did not understand gravity, and neither did anyone else. But other scientists of his time either didn't appreciate the severity of the failing or didn't pause to consider the implications. But because he did not understand gravity, and he admitted as much, Einstein challenged the consider gravity to be a force of one body acting on another, force that mysteriously did not require actual contact. After Einstein, the language changed. Gravity was cast as a curved space-time. How can the Earth pull on the moon without touching it? It doesn't. It doesn't pull on the moon at all. It exerts no force. Instead, the Earth bends space, and the moon tumbles freely. Black holes are a space. Far from a black hole, the curves in space are the same species as those around the sun, or the moon, or the Earth. If the sun were replaced by a black hole tomorrow, our orbit would be unchanged. The curve we would fall along around a black hole sun is nearly identical to the curve we fall along around the actual sun. Of course, the perpetual dusk would be apocalyptically cold and dark, but our orbit would be just fine. The Earth is on average about 150 million kilometers from the sun, which is about 1.4 million kilometers across. In comparison, a black hole the mass of the sun would be 6 kilometers across. You can approach much closer to a black hole and remain unharmed than you can to the sun, despite a black hole's reputation for voraciously consuming all and sundry. Only really notice a radical difference between the space around a black hole and the space around the sun when you get within a few hundred kilometers of the center of each. And you can't get that close to the sun without incinerating. Bore inside the solar plasma, and the gravitational pull of the sun eases off. As you approach the center, you leave behind some of the sun's mass. The curving of space inside the sun's atmosphere becomes more gradual as the mass beneath you diminishes. By contrast, no matter how close you approach to a black hole, the source never diminishes. The curving only gets sharper. Black holes are special because you leave none of the black hole's mass behind you. It is as though all of the mass is concentrated ahead of you, always. You can approach infinitesimally close to the center of a black hole and still feel all that mass in front of you. Keep a safe distance from an unobtrusive black hole, and you will neither be torn apart nor sucked up. Black holes just are not the catastrophic engines of destruction they're portrayed to be. At least, not until you are recklessly close. Then admittedly, circumstances can get harrowing. Even if you approach boldly close, within several widths of the black hole, you could set up your space